move to this section. And just again, as we covered pipelining, data path control, finished structural hazards, finished data hazards. Now we're talking about control hazards. And here is an example that we're going to look at. We're going to look at where a branch is supposed to be taken. So it's supposed to be resolved as taken, but we predicted that it was not taken. Branch. We're predicting that it's not going to be taken, so we're going to fetch this and. But in reality, we figure out in the next clock cycle in decode that the branch should have been taken. So we're going to flush this and fetch this loop. Okay. So here's our branch, right? And this is the and that is being fetched while we're trying to figure out the results of this branch. And this was our predicted instruction. And at the end of decode, we figure out that our registers are indeed equal. So over here, with the new target address, I'm going to update PC. On the next clock cycle, we'll fetch the correct instruction, which was the load word. And then the hazard detection unit will turn this and into a no operation by setting its control signals to 0. Right, so that's our branch moving forward. This is the no op that set all of the register values in this register to be 0. And then this is our load word because we changed PC. Right? So this was the 3 cycles of the single cycle diagram, right? For the code to show that we predicted not taken, but it ended up being taken. So we have to flush that instruction out of the pipeline. Right, so the impact of reducing the cost of a branch hazard. So branch detection, we move to the instruction decode stage, right? When we predict, we're going to guess one direction. And then if we are wrong, we need to flush the incorrectly fetched instruction. So if we have the correct instruction though, we lost 0 cycles. But if we're wrong, it costs us 1 cycle. We need to flush and restart with a new instruction if we were indeed wrong. So this clears the instruction field in the instruction fetch and decode pipeline register, creating a no operation. So one thing that we can do in terms of calculating performance based on this, let's just assume that we are right 50% of the time. CPI for a branch would be 1, it's just 1 CPI half of the time, right? Because half of the time we're right and it doesn't cost us anything. But the other half of the time, it costs us 1 additional cycle because we have that flush instruction that turned into a no operation. So the overall CPI for a branch, if we're right 50% of the time, in this case, would be 1.5. So here's some more things that we can talk about in terms of the performance equation. If 20% of instructions are branches and the other CPI of instructions is 1, so we don't incur any data hazards, anything like that. We're just evaluating the performance impact of the branches. Then we would say that our total CPI is just like before, I have this instruction type, which are branches that make up 20% of my instructions. And it's a CPI of 1.5, and all of my other instructions have a CPI of 1, they're 80%. Overall, for that program on that CPU, the CPI is 1.1. Alright, so here is a different solution that's we didn't fully cover. We talked about what it is, but it's called the delay branch. And the way that we're going to solve the branching problem is by filling the slots after the branch with an instruction that executes no matter what the decision of the branch is. So we're just finding some independent instruction of that control hazard, and we're going to execute that right after the branch so that we can have that one cycle of time to figure out what is the branch, is it going to be taken or not taken, and then we can immediately, after that one cycle delay, fetch the correct instruction. There's no need for prediction. Okay, so here's how it would look in terms of code. So this would be before, right? We have this instruction that doesn't depend on the branch, and the branch also doesn't depend on it, right? They are both reading from S2, but this add is not writing to S2, which is a key part. So rather than executing this instruction before the branch instruction, we can execute the branch instruction and then start the execution of this instruction. And we resolve the branch and decode, so the very next cycle, and then we fetch the correct instruction based on the branch outcome. So this is also a potential solution, but the downside to this is it might make sense for our very simple pipeline with 5 stages. We have 1 delay slot, but real pipelines are up to 20, 30, sometimes even 40 stages. You would have delay slots 5, 6. There would be a lot of delay slots to fill. Yep.
Would that be done in software or hardware to find the delay slots?
So it could be done in either. So, but that's something in terms of the hardware side, it's something that's one of the research presentations we covered, because one of the more advanced techniques in computer architecture is out of order execution. So if you have out of order execution and you're fetching multiple instructions, then you can figure out on the fly in the hardware which one of these instructions are independent. And you could put that in these delay slots. But in reality, we don't have these delay slots anyways, because there's just way too many of them. You're not going to find 5 to 10 independent instructions.
Then you'd have to make something that would also have it not throw like a dependency. For this example, it looks like it would mistake that it would be dependent if you shoved it in the delay slot.
Exactly.
Okay.
It has to be independent of the branch instruction control as well as the branch instruction itself. Right? So like you're saying, if this was writing to S2, you can't put it in the delay slot. It's independent of the control, but it's not independent of the branch. Okay. So if we can find an instruction that fills this delay slots, then there's no impact. But if we can't find an instruction for this delay slots, what goes into the delay slots? Like if we can't find an independent instruction, what would take its place?
So
A no operation. Okay? And like I mentioned, it's much harder to build pipelines with more stages. So this is basically not done. Okay. So here is a question that we can think about. Let's see, your poll code today is, what is it? 988, so answer immediately. And then when you're done thinking about what can go here into the delay slot, change your answer from A to B. Just as a reminder to change your answer from A to B. You are done thinking about it. Okay, so most of us are done. So let's just talk about this together. Okay. So anyone want to tell me their process? What, yeah,
The first thing I did is look at the branch and see what it's comparing. So it's comparing register 6 and register 7.
Mhm.
So then I'm gonna have to look at the destinations of the, like, one by one going previous. Is it 6 or is it 7? If it's 6 or 7, I
Mhm.
can't use that
Mhm.
because that's what's being compared. So
Mhm. So the branch is dependent on them, right?
the branch is dependent.
So
on them.
that's
So you go
three
4, 3
and 4.
3 and 4,
right?
it's dependent because, yeah. And then you go to 2 and you're like, okay, well, that's running to 9. So 9 looks good. I did. Yeah, I did consider, but it doesn't really matter here whether or not, like, it had any dependencies, but it obviously doesn't. So that I figured 9 was probably, or that instruction add 913 was a good one.
What about 1? This add.
Thought that one was the best option because the second and register 9, if we place that one where the delay is, then the 6th instruction will be dependent on that one. So I think number 1 is independent of all the instructions before and after.
So it's not important that this instruction need to be independent? Because this add, if you chose it, would be executed before this instruction. Right? Yeah, question?
I just want to point out why I think one would be bad to do there.
Mhm.
7 is changed in step 4, and if you put it in after 5, you would have a different 7 than what you would have
Mhm.
where it is.
That's right. So 1, you actually can't use. Yeah, because of this instruction 4. But 2, you can use. The other thing that we want to point out is we were only looking at the instructions before the branch, right? Because all of these instructions after the branch, assuming that they write to a register of some kind or write to memory, they are dependent on the control of the branch, right? So we're going to use this add 913 as our delay slot. So you can see just from this small example, like we were only able to find one independent instruction. So we needed to find 5. Imagine that it's going to be a hard task. So solution 4, which is the approach that is used in modern processors today, is going to be branch prediction. So we already talked about static branch prediction, right? We are going to always predict that it's taken or always predict that it's not taken, right? But there's also dynamic branch prediction. So we're going to use hardware to measure the behavior of the branch and its history. And then we're going to assume that the future behavior will continue the history of that branch instruction. And if that branch instruction was, say, not taken 2 times in a row, the next time we see it, we will predict that it will be not taken again. Okay? So we're going to use hardware to save this history and use that to guide what our prediction should be. So how do we keep this history of each branch? We're going to have this branch prediction buffer. So we're going to keep a list of the recent branch instruction outcomes of taken and not taken. And this list of branch instruction is 32 bits address, right? If I wanted to keep an exact history of every single branch possible, my table would need to be 2 to the 32 entries. That's too many entries, right? So rather than having a place for every single possible branch, we just use some amount of the lower bits of the branch address and use that to index into some smaller table. And this will result in some branches will correspond to the same row in that table, and they will fight for that entry and that history of the table. But that's better than not being able to create this table that would hold history for every single possible branch. So to execute a branch instruction, we check the table, see what the expected outcome is based on the history. And then that's what we predict. And we start fetching based on that prediction. And then in the next clock cycle, when we resolve from the branch, if we're wrong, we can flush. And we fetch the correct instruction. But if we're right, then we don't have to do anything. So this is going to give us limited precision, but it is only a prediction. And for the most part, we hope that this would be better than stat prediction. So here is an example of our dynamic branch prediction. And in this example, we're going to assume that our table of storing the history is only 1 bit. So it only remembers the previous result. So the previous result was taken, it's going to predict taken. If the previous result was not taken, we're going to predict not taken. We can only look back into history by 1 previous output. So if we have this branch here, we have this for loop and then this for loop. The question is, how many times will the prediction be wrong for the inner loop? What do we think? And we're assuming the first prediction is that it's going to be
It folds in on once. The end of the loop.
at the end of the loop, right? Yeah. But if we have this outer loop, so the very first time we come here, first prediction is taken, right? And then we loop 8 times and it's taken, but then on the 9th time, we're at the end of the loop, so it should be not taken. So now the history for this branch says I'm not taking. So when we come back to from this loop and come back here the second time, I predict not taken, right? Because that's what it was before. So I get it wrong for the first one. And then I start taking, and I start getting it right, right? But then at the end, I get it wrong at the end again. So because of this other loop, on average, this is getting it wrong twice.
For full.
Yeah, for the full execution of this code. But the very first time, yes, it is just once. So this is a downfall of this 1-bit predictor. Okay, because if we could just remember 2 of the history, then when we see that the very last one is not taken, yeah, we'll get that one wrong. But then when we come back up here, we'll still predict it again. So here is our 2-bit predictor. In our 2-bit predictor, because we have 2 bits, we can encode 1, 2, 3, 4 states, right? So this state is what we would call strongly taken, right? The last 2 or so instructions have been taken, right? So that means that we feel very strongly that it should be taken again. But if we then see that we are wrong and we get not taken, okay, we move to weakly taken. Because we are still predicting taken because it was only 1 that changed. Okay. We were wrong once. And then if we're right again next time, we'll move back to strongly taken. And if we keep getting right, we'll just stay in strongly taken. But if we're wrong once, and then we're wrong twice, we now move to weakly not taken. And then if we're wrong again, we move to strongly not taken, right? Because now the last two have been not taken. So this is now what's my recent branch history is telling me to do. Right, so you have these two bits just specify, am I in strongly taken, weakly not taken, or strongly not taken, right? So we can have a better idea of the past history with 2 bits rather than just 1 bit. So here is an example. So we have this, assume the following 3 sequences of branch patterns. Assume the initial predict taken for 1-bit predictor and strongly taken for a 2-bit predictor. The question is, what is the accuracy of each? So let's do this together. We can do the 1-bit predictor first. So initial prediction for our 1-bit predictor is taken. So I haven't seen anything, right? It was initialized to take it, so I'm going to take it. And now, when I see this second branch, like the second occurrence of the branch, my previous one was taken, and it was right? So I'm going to predict taken again. And I'm right again. So I don't update the predictor. I predict taken again. Again, we're right. We don't update the predictor. So on the 4th time, we are still predicting taken. And we are again right. So we don't update the predictor. So for our 5th prediction, it's still taken. And now we're wrong, right? So our next prediction would be not taken for the 1-bit predictor. So now for this sequence, first prediction as always, are we right? So taken again. Were we right? Yep. We predict taken. Were we right this time?
Not.
So then my next prediction is updated to be. Were we right? No. So now my next prediction is taken. Right? All right, first prediction is right or wrong?
Wrong.
And then my next prediction becomes and right or wrong.
Wrong.
So now my next prediction becomes right or wrong.
Wrong.
Next prediction becomes
Not taken.
again wrong, right? So we predict taken next, and again it's wrong. So if it has this pattern, not taken, taken, not taken, taken, not taken. Even if we're right the first time, we will be wrong for all subsequent times. So this is a pattern that we see often with these statements as well. So the 1-bit predictor is very bad at that kind of pattern. And that's what we see here too. This is a very similar pattern, right? But if it is a long string of takens or a long string of not takens, which is also a very common pattern, right? It's what we saw with the for loop, right? If you're just incrementing. So it's pretty good at that. So let's see the 2-bit predictor. We're strongly taken is what we're initializing to. So if we're in strongly taken, what's our prediction? And or was it right?
Right.
So do we move states? Yep. we just stay in strongly. And because we stay, it's taken. We're right again. So again, we stay, right? And we're right again. So we stay. And we're right again. So we stay. And this time we're wrong. So we actually need to do some update to the predictor, right? Which state did we move to? Yeah, weekly taken would be the next state. Right. So now this string taken first, right? We're right. We stay strongly taken. We're right again. We stay strongly taken. We're wrong. We go to weekly taken. Weekly taken, we still predict. And now we're right. Right? So we move from weekly taken to strongly taken. And then we're wrong, so now we move back to weekly taken. But in this case, we are still slightly better than the 150. Right? What about here? Predict taken. And we move to weekly taken. Taken. We're right, so we go to strongly taken. Predict taken. We're wrong. Move back to weekly taken. Predict taken. We're right. Move back to strongly taken. Predict taken. We're wrong. Move to weekly taken. Right? So it takes 2 wrongs in a row in order for us to switch from taken to predicting not taken. And none of these have that pattern, right? Which is why we are always looking for these patterns. All right, so this is your full question now. So answer it on your own first. You have this pattern for the branch history. And we're assuming that we are initializing to strongly taken, just like we did for the other example. You answer this on your own first. don't see answers changing anymore. Anyone still thinking about this? Right, we are not quite at the threshold, so do talk to the people around you. See how you got to your answer. See if we can have some movement towards the right answer.
By the time the one takes the two, because they're just small, it only be the last one, because there's 10 in a row. Exactly. Yeah. All through.
Okay, just as a reminder, do change your answer if you were convinced to change your answer. Okay, so we did have some movement towards the right answer. Right, so my initial state is what? Strongly taken. So if I'm strongly taken, my prediction is taken. So we like all of them so far, right? And then my actual result was, so I stay strongly taken then. So my next prediction is
Taken.
yes, taken. And it was right again. So I again stay strongly taken. So my third prediction is taken. So we no longer like A or C. Right? And my result was not taken. So I was wrong, right? So my new state is weakly taken. So I still predict taken. So we still like B or D. And our result was correct. So we move from weakly taken
Strongly.
to strongly taken. And predict taken. We were wrong. So we move to weakly taken. So we still predict taken. We're wrong again. So now we move to weakly not taken. So the next prediction should be
Not taken.
not taken. So we like D. And then what's my ending state?
Strongly not taken.
Strongly not taken, right? Because this not taken was correct. So this is D. All right, so this is a very simple branch prediction scheme. The latest branch predictors are significantly more complicated than this 2-bit predictor. And it's using a lot more advanced correlating techniques and much larger structures, including, it says AI, I don't like the word AI. It's using machine learning, it's using a perceptron. The largest machine learning based branch predictor that I've seen is using a perceptron. Perceptron is very small. That's not using like convolutional neural. Because we need to fit in the clock cycle of the CPU, right? And it can't be too large. So one of the topics for the research presentation is branch prediction. So if you are doing branch prediction, we covered 1-bit predictors, 2-bit predictors. The paper that you are reading is covering many other techniques. Just teach us about a couple of them, whatever fits in 13 minutes of lecture. And the paper is just a starting point, right? So one of the simpler ones that you can start with is G-share. G-share is just going to correlate other branches together. Because this branch might be dependent on this branch. Like if I take this one, maybe this one is going to be for sure not taken. So just as a hint for if you guys are, whoever's doing the branch prediction. And in general, for everyone, the paper is a starting point. The goal of the presentation is to do exactly what I'm doing here, right? Teach us the topic. Give us a short tutorial on it. So they're using these patterns, the local history and recent other history, so the global history of all branches to make predictions. This is G-share. So just as a recap, right, it's pipelining, we're improving instruction throughputs, not individual instruction latency. Data hazards can and probably should be handled by hardware, but you can handle it in software. And should be because we figured out that that's the best way to get performance. So most modern processors have hardware for stalling and forwarding. And the other reason that it should be handled in hardware is because another one of the research presentations is on out of order execution. If you have out of order execution in your hardware, you need to be able to figure out these dependencies. So control hazards can also be handled by hardware or software. But most modern processors are going to, again, do this in hardware. Because like we talked about with the branch delay slots, it's very hard to find those independent instructions. Maybe find 1 or 2, but finding 5 to 10 of them, basically impossible. And our performance equation is exactly the same, right? We have instruction counts, we have CPI, and our base CPI for pipeline architectures with very, very large instruction count is 1, right? Because we finish 1 instruction every single clock cycle. But we will see later in our lectures that because of these data hazards, because of branch control hazards, and then in the next chapter because of the caches. So exceptions might close your program. So, okay. So because of caches, we're going to have to calculate what the CPI really is. And we already saw an example, right? Just from this lecture. If our branch predictor was 50% right, and our branch instructions are 20% of instructions, we saw that. If it's right, it's 1 CPI. If it's wrong, it's 2. So a branch is 1.5, and then 0.2 times that 1.5 plus 0.8 times 1 gives us 1.1 overall, right? But you would have to do that same process for what percentage of my instructions are, say, R-type, right? And what percent of those instructions are dependent on their previous instruction. And what is my penalty? Okay. So for R types, there's no penalty. We can forward that in our architecture. But if it's a branch after the R type, it's a penalty of 1. Load word, if it's R type dependent after, penalty of 1. If it's a branch after, the penalty of 2, right? So you can calculate this new CPI based on those percentages and the penalties. All right, so for next time, you should be reading chapter 6.8. Just as a reminder, I have not moved this due date, but this due date will be moved to Monday because no class on Friday, right? Friday is Veterans Day observance. Actual Veterans Day is Saturday. We're observing it on Friday. So don't come to class on Friday. I will not be there.